In this series of videos, we're going to introduce one of the most important things we'll learn throughout this first semester, and that's L'Hopital's rule. I think the most important thing we've learned so far is the chain rule, because it comes up a lot throughout the entire course, but this might be the second one because it comes up a lot as well. Before we get to L'Hopital's rule, there's one thing we have to do, and we're going to talk about local linearization. So what we're going to do is we have this function. We have some function that looks like this. And if we think about the tangent line of the function at some point, maybe we have this point here, and its tangent line is going to be like that. When we're looking at this tangent line, if we're looking close to the point we care about, like right here and right here, the tangent line is basically going to give out the same values as the original function. Once I get farther away, there's this big gap between the tangent line and my original function, but all these values that are close to my original value are pretty much the same as the original. So what we can do is we can use the tangent line in order to approximate the function close to the starting value. All right, so if we're plugging in 1, we're not going to use it to approximate 10 because 1 and 10 are pretty far apart. But if we were plugging in 1, we could approximate, say, 1.1 using the tangent line. All right, so let's see how we would do that. All right, so for some differentiable function, again, that just means we can take the derivative of it. We have f of 1 equals 3 and f prime of 1 equals 4. All right, so first we can do is make our tangent line, and from this piece of information, that is our point. So the point on our graph is going to be the x value is 1 and the y value is 3. And our other thing, the derivative, remember the derivative is the slope of the tangent line, so that's going to tell me the slope of my tangent line is 4. All right, so from that information I can make my equation. And my y value is 3, my slope is 4, and my x value is 1. I distribute that and add 3 to both sides. So my tangent line is y equals 4x minus 1. And what I said in the previous slide was this tangent line basically approximates the original function for values close to 1. And 1.5 is fairly close to 1. So now that I have the tangent line, instead of plugging in 1 into this expression, I'll plug in 1.5. All right, 4 times 1.5 is 6. 6 minus 1 is 5. So my approximation for my original function is that when I plug in 1.5, I'm going to get 5. The chances of that being exactly right are really slim, but 5 is going to be a good approximation. Maybe the actual value is like 5.2 or 4.7 or something like that, but 5 will help me approximate using this tangent line. All right, one more example. All right, f goes through the point 3, 5 and has derivative given by that expression. All right, can we use that to approximate 3.5? Well, the first thing is they tell us the point we have, and now we just need to figure out the slope. All right, but the slope comes from the derivative. And if we think about our original point, the x value we care about is 3. All right, so the whole problem for our original tangent line is our x value is 3, so I'm going to plug that into my derivative. And then just simplify. And I get 3. So my point on my original graph is 3, 5. The slope of its tangent line at that is also 3. So I can make my linear equation now for the tangent line. I distribute that 3 in and add 5. All right, so this tells me the tangent line to my graph at the point 3 is 3x minus 4. And again, that tangent line is going to be really similar to the original function at the points close to it. So we could plug in 3.4. All right, plugging in 3.4 into my original function will be similar to plugging in 3.4 into my tangent line. So now I'm going to plug 3.4 into my tangent line. 3 times 3.4 is 10.2. And I get 6.2. All right, so my approximation of my function is 6.2. Again, it might not be exactly right, but using that tangent line, I get a guesstimate of what the value should be. All right, so this is linear or local linearization. You're basically using a line, which is the tangent line, to approximate this bigger function. All right, it just means I need less information to get a guess for what my function should be.